check prints just the type. Okay, now, going on quickly. We are not going to have time for very much. Actually, let me ask you. I can talk through some of the rest of this file for a few more minutes. Or we can stop at this point and give you a chance to get your fingers dirty trying a few things yourselves. Which would you prefer? So let me take a quick vote. I'll ask for both options this time. So how many people would like to just hear a few more minutes of me gabbling on about what's in this file? How many people would prefer to stop and just play with exercises? All right, about 50-50. So I'm going to choose to continue talking for a minute and then stop. So that's just like compromising on 9:30. Let me kind of skip forward, just kind of telling you what's on each screenful. So we defined the Booleans and some functions over them. Here we define the natural numbers and some functions over them. And the main thing that this is showing is pattern matching, which is basically just like pattern matching in your favorite functional programming language. So not too much interesting there. One thing to note is that when we do recursion over natural numbers, we use, or over any, whenever we define recursive functions, we use the keyword fixed point instead of the keyword definition. And Calc will check that this fixed point is terminating because the n prime that's being passed as the argument to even b is structurally a subphrase of the original input n. Okay. We can define infix notations using some notation definition facilities. Nothing too interesting there. Okay, now we come to more interesting theorems. So the theorem here is nothing very different than the example we had before, the examples we've had up until this point. Just the type that is being claimed to be inhabited is a bit more interesting. It's got a for all in it. And then the equality proposition under the for all has some variables. But even so, because of the way plus is defined, it's recursive on its left argument, this theorem can be proved just by simplification. And I'll let you see that for yourselves as you're playing with this. Okay, so some theorems we can prove, some interesting theorems, slightly interesting theorems, we can prove just using the facilities that we've seen so far. Others need a little bit more. So here is a little bit more interesting theorem. So this theorem is a hypothetical theorem, and it says n plus n equals m plus m. So that's not true just by simplification. It is true by rewriting, that is, replacing equals for equals. And the way we do it is, so here's the proof. So the first thing we do is we use the intros tactic. I skipped over the explanation of it. Intros moves some variables from the goal to above the line, which is the assumptions that we're using to try to prove the goal. Okay, so now the goal is prove this under those assumptions. Those assumptions are not too interesting. More interesting is the assumption that n equals m. And we've given it a name, h. And now on the next line, we're going to use h to rewrite the variable, let's see, we're using it left to right. That's what that arrow means. You can also use it right to left. We're using it to replace the left-hand side of h by the right-hand side. So we're going to change the n's to m's in the conclusion. And now we can finish by reflexivity. Okay, so this is proof by rewriting, and this is the fundamental way of using equality propositions, equality hypotheses. All right. Sometimes, often, usually, the thing that we want to prove about a number depends on which number it is. So there, we're going to need a way of saying, well, is it 0 or is it successor of something? And the way we do that is with this tactic called destruct. So here's a simple thing to try to prove. So BEQ nat is a Boolean function that tests whether two numbers are the same, returning a Boolean. And we'd like to prove that when n is a number, n plus 1 is never equal to 0. How can we prove that? Well, we can't prove it directly because we can't simplify the last line because n is a variable. But we can prove it by case analysis on n. So if n is 0, then we can simplify. If n is non-zero, then we can't completely simplify, but we can simplify enough to know that BEQ nat is definitely going to return false. Okay, so the simple reducer is able to deal with expressions with variables in them as long as the variables are kind of buried deep in the term. It can reduce the expression around them. So that's what's happening here. So now we have two subgoals, and each one of them is solved by reflexivity. Okay, here is a little bit of magic that you skip over. But the way that you use the magic that we just skipped over is when you're doing proofs by cases or proofs by induction, it's convenient to name the cases. It's convenient to be able to write, this is the case where B is true, this is the case where B is false, if we're case analyzing a Boolean. And so this case tactic with a capital C is just a little bit of, well, it's a little bit of programming in Coq's tactic programming language, which we'll come back to in a few lectures. So you don't need to understand the details of how it works, but it's a little program in Coq's internal language that defines this case tactic. And you'll see that as we're, I'll just show you now, as we're working through the proof, you'll see that the proof state includes this string B equals true that helps stay oriented in which case of the proof we're working on. And when we finish the case and move on to the other subgoal, that string disappears, and now we can add another string using this, using the case tactic again. Okay, so last thing, and then we'll go or hang around and do some experimenting, is induction. So simple case analysis of numbers is enough to prove some things, like the little theorem we looked at a minute ago. But to prove interesting things about numbers, you need induction. To prove almost anything interesting about numbers, you need induction. So here's how it works. So you have something in the hypotheses in the environment of type nat. Type nat is an inductively defined type. We introduced it using this inductive keyword. And remember, at the moment when we did that, an induction principle was defined. The induction tactic uses that induction principle to generate appropriate subgoals corresponding to the cases of a standard inductive proof. So we say induction n, and then this as thing is just doing a little bit of helping with naming. All right, so 30-second digression. Many of the tactics in Coq involve introducing variables. If we just say, for example, induction n, it will automatically choose variable names in the subgoals as it likes. Here, what it's going to do is choose the name n for the number in the subgoal. But that's a weird thing for it to do. I find that a confusing way to think about the proof, because the n in the subgoal is actually the predecessor of the n that we originally started out with, because in that subgoal we're dealing with the case where the original n has the form successor of something. So what Coq has done is, since we're not using the original n anymore, it's just reusing the name for the thing that the original n is the successor of. So that's just bizarre. So I recommend always using this as annotation on the induction tactic, which allows you to control its choice of variable names. Okay, so the vertical bar is saying there are going to be two subgoals. I don't care about the first one because it's the zero case and there isn't any variable binding. The second case, I want you to use n prime, not n, as the name of the variable. Okay, so now let's look at what happens. So when we do the induction, we get two subgoals. The first subgoal is to prove the theorem that we're interested in the case where n is 0. And that proof is easy by reflexivity. And then the second one is to prove the thing that we're interested in where n prime is some number, and we get an induction hypothesis that says n prime plus 0 is equal to n prime. All right, so this is a standard inductive proof, Coq style. Okay. And that is all I wanted to tell you about this file. So, so those of you that want to, let's stay around for a few minutes, and why don't you take a chance to do a few exercises. So at the beginning of the file, you'll find some simple functional programming exercises. Go ahead and do them. They'll take you 5 minutes, and they'll get the syntax, the concrete syntax under your fingers. And then there are some more interesting exercises. In particular, there are several, I think maybe 3 recommended exercises. The first 2 are easy. The last one is a little bit more challenging, and chewing on it will give you a little bit deeper experience with thinking about how to do things the Coq way. So, so I recommend doing at least all of those recommended exercises, and as many as you have time for in the next few days of the other exercises in the file. You'll also find, so what I was showing you just now was the terse version of the file that I like to lecture from. There's a bunch more text that explains all of this in quite a bit more detail in the version of the file that you should look at. Final note, the version of the file that you should look at is the one that is now, as of 1 hour ago, linked from my homepage. So, so if you go to my homepage and follow the link to Software Foundations, you'll find a brand new version that I just exported this afternoon of the lecture materials, which I may re-export slightly newer versions over the course of the week, but they'll be different only in small ways. So that's the up-to-date version. Okay, have fun. Any questions, first of all?
Something like what the keyword means, something is there shortcut to pull up
like a theorem or something like that? Plenty of text in the chapter. You'll be fully explained.
Okay, and the dots, they are like sequencing points that just separate
the periods at the end of commands, they're Coq, that was the end of a command.
Two quick questions. Number one, is there any kind of a cheat sheet on the Coq's ID itself?
There must be a cheat sheet on the Coq ID.
Number two, is there any written instruction for someone who does not know Emacs for configuring Emacs and Proof General? Yeah.
And there are many people in the room that can help you with that, and that love to have new Emacs users.
About the file version, on the webpage it has the date 17th of July 2012, but the files that are downloaded have the date as April 2nd, 2012.
Yeah, that's fine. So the front page of the book says 17th of July, but the files themselves have older dates. That's because those files individually haven't been changed for a little while. So that's fine. Any other questions? Okay, have fun.